Today's screencast is on some basics you'll need for 3091, and the first basic has to do with Newton's first law. Newton recognized that in order to get a body to change its momentum, you have to apply a force. So mathematically, we write that this way. So the little arrow above each, the force and the momentum, means those are vector quantities. They have a direction to them. And the derivative means that the change in time. So on the right-hand side, you see that the momentum is changing in time. And on the left-hand side, you see it's equal to the force. So Newton said the force required to change the momentum a given amount in a given time is given by this equation. Now, momentum is a vector quantity, and it's really just the product of the mass of an object times its velocity. And velocity, of course, is a vectoral quantity. It's got a body is moving in a particular direction with a particular speed. And you can see that the momentum has exactly the same direction as the velocity. So if you substitute that into this expression, you have that the force equals the mass times how fast the velocity is changing with time. And we say that the acceleration is equal to the velocity's change with respect to time. And so now you get the familiar equation. Sorry, that should be a vectoral quantity also, m times a. Now, lots of times the body's motion is confined to one particular dimension. So oftentimes you'll see this written as F equals ma, recognizing that if the body's confined to motion in one direction, these don't need to be vectors anymore. They're just scalar quantities. Now, the units are very important here, so we always want you to keep track of them. If force equals ma, then the units should match on each side. So the mass, of course, has units of kilograms. And acceleration has units of, well, the velocity is meters per second divided by time. So then the units of acceleration had better be meters per second per second. So you put the square there. So that means the units of force had better be kilograms, meters per second squared. Now we call that funny combination of units in MKS. We call that the Newton, in honor of Sir Isaac Newton, of course. The other situation that we will run into when forces and momentum come up, it has to do with bodies circulating or orbiting around another. So let's say we have the nucleus of an atom. As you know, one old model of the situation in an atom is that we have an electron in an orbit around the nucleus. And that electron in an orbit, of course, has a velocity. Let's call it v1. In the next instant, the electron will have moved in its orbit, and now it will be here. We'll call that v2. Now, the magnitude, if it's in a stable orbit, of course, doesn't change. The velocity is staying constant as far as its magnitude goes. But it has to, obviously, change direction. Now, remember, in the vectoral sense, the force and acceleration are both vectoral quantities. Acceleration is the change in the velocity versus time. That means any change, not just in magnitude, but also in direction. So this orbiting body, even though the velocity magnitude is not changing, its velocity direction is, so there has to be a force being placed on the electron as it orbits. We call that the centripetal force, and its magnitude has to be the mass of the electron in this case, or any orbiting body, times the acceleration that occurs due to this orbital motion. And without doing all the mathematics, it turns out that the centripetal acceleration, as we call it, depends on the magnitude of the velocity. So v here without the vector sign just means the magnitude of the velocity divided by the radius of the orbit. So that means the centripetal force to keep it in this stable orbit is the mass times its acceleration. So there you have it. The key equations here, of course, are this and this.